2400 watts, but on the graph it'll say that you only reach about 2300 watts in every experiment. So we don't know if that's just a problem with the graph or if that's just what it can achieve, the maximum that it can achieve. And then you can see here where we brought it down to 1200 watts and then again to 650. Again, this is another graph that is produced with the results. So on this side, we have the heating curve, so you can see the reboiler, where it was heated up. And then this side is where it started to cool down, where we decreased the reboiler settings. So you can see here power turned up to 2400, where it started to increase. And then we turned it down from 1200. So you can see that there's some of them are slowly decreasing, but not all of the trays. And this is where we turned it down to 650. And then on here, there's tray 1 is the blue, and then tray 2 is red. And then this over here is trays 3 through 12. The experiment wasn't run long enough to show the decrease in all the rest of the trays. So they're still at 100 degrees. They're still all boiling. And this is a graph of the cooling water temperatures. So you have your supply. Your supply is the red line, and then you have your return, which is the green line. And then these peaks should correlate with the same time that we increase and decrease the reboiler voltage. So you can see our delta T. These are the observations that we made from experiment 1. At 2400 watts, it takes about 30 to 35 minutes to reach boiling. However, we let it stay on 2400 watts in other experiments for an hour just to achieve a steady state. In this experiment, we just let it reach boiling and then we dropped it. And we started this experiment at room temperature water. So these are some of the other observations that we made. The cooling water flow rate was observed at different reboiler settings. So the 2400, 1200, 650, it's about constant. You know, there's a little variation, and that's probably operator error where we're taking the bucket, filling it up, taking the time. And then in most of the experiments, we notice this phenomenon known as flooding. In this picture, there's the water level line. And this occurs when the wattage is too high, so the liquid gets trapped in these ports, and then because the vapor is going up too fast. So this is the temperature probes, and this is where in these ports the water gets trapped from where it's bubbling up and the vapor is going up too fast, and the liquid gets trapped in those ports. Each individual tray has its own temperature probe. And this is just the phenomenon to compare it to two ports that are normal. So this one, there's a little condensate, and then this one, there's just a little liquid level just from where it had bubbled up into it. Whereas this one is completely full. This is our thermal data for experiment 1. We have our average heat release, and then our average heat from the condenser, and then the uncertainty in both. This is a schematic of the heat removed from the column. So each tray, there will be heat removed. And you put in heat into the reboiler, and you also have heat removed from the condenser. So, let's see. Yes, I think it's what? No, correct. Oh, we had the tray temperatures in here where we showed the. Alright, so we estimated the average heat removed where we decrease the reboiler power setting, so you can see all the delta T's for the different peaks. And the thermal data again, you have your average heat removed, and then your reboiler. So this is at the different settings that we set it to, and then this is the average heat removed from the condenser, and then certainty in both. Again, the schematic for the heat removed. And this one, we can only determine tray 1 because it's the only one that significantly dropped off. And it was 200 watts. So the heat removed by the condenser, it changes for each reboiler power setting. And then again, the system takes a half hour to achieve boiling. And the heat loss for the other trays were not able to be determined from the data that we collected. Experiment 3. All right. We filled the reboiler with 13 liters of water and 1 liter of methanol. And we performed this test at different settings, again, 2300, 2100, so on and so forth, until we got down to 400 watts. And the reflux was set again to 100% in this reaction. The reboiler power graph. Again, you can notice that we have this fluctuation, and we are not certain what causes that. So, but we just averaged it for each system. Fluctuation. The tray temperatures. Notice in this experiment, you can significantly see where the tray temperatures drop off versus the other experiments when we didn't let it run long enough, or we decreased the power wattage too soon. So on here again we have the heating, and then this is your reboiler, and then tray 12, 11, 10, and if you go down, 9, 8, 7, 6, so on and so forth, all the way down to 1. It's kind of hard right here to differentiate between trays 1 and 9 because they are so close. But if you go a little bit closer to like 100, you can notice this one is tray 9, and then tray 8, tray 7. So you can kind of estimate the average heat release from that. And again, the cooling water temperature graph with the different delta T's at the peaks. And again, our power settings for the reboiler and the average heat removed from the condenser and the uncertainty in both. For this experiment, we could determine Q1 to be 200 as before, and then we estimated the other trays from the tray temperature graph. Since tray 1 significantly dropped off, or not true. Yeah. So tray 1 is here, since it dropped off pretty much first past its highest peak, we could estimate that. And then the other ones we averaged because they all drop off at about the same time.